Okay. Okay, now we will explore what is back propagation. Yesterday we discussed forward pass, and I just used the same thing. I put together everything in a visually appealing thing here. Okay, the neurons. Look here, I just minimize it so that it will be more visible. So here you have the input neurons, and then the hidden layer neurons, and then output layer neurons, and this is your, what is that? This is your bias, right? There are two neurons that are related to bias. So each synapses, we mentioned about the weights, weight 1, weight 2, weight 3, and weight 4. For each weight, we have randomly assigned some values, 0.15, 0.20, something like that. And right, so these, the hidden layer receives the input from input layer. How it receives? Upon receiving these values, what it does is it carries out two tasks. The first task is multiply each network's weight by the input value plus, right? It takes the product of each network, right? Each lines, each synapses weight by the input value. That is how it works, right? It sums all the things. Okay, so weight 1 into input value plus weight 2 into input value plus weight 3 into input value plus, so that is how it works. Okay, so first it sums all the values and then it does the sum. The second step is, once it has been done, it applies the activation function on the Z. So Z is holding the sum of all the synapses product of the corresponding weight with the input neuron value. Okay. So 1 second. Got it? Like I said yesterday, you don't have to worry about this 0.15. So this weight 1 and the weights are all computed by the model automatically, the neural network model. We don't have to worry about that. Okay, it is computing it everything automatically. That is also the reason why we call this as a parameter. Weight 1, weight 2 are all called as parameter. Now I will just write the same thing, the hidden layer. Okay, because you might have I call the hidden layer first neuron as a net H1. Okay, I'm talking about this one. Okay, this one. Okay, net H1. How the two-step carried out, right? The two tasks will be carried out. Or W1 into I1 plus W2 into I2 plus B1 into 1. So here 0.15 into 0.05. The reason why I'm writing again is we are going to compare this once we are done with the back propagation. Okay, and weight 2 is W2, right? So this one and this one. W2 is your 0.20 and 0.20 into 0.1. So this is your input 2 and input 1. So here this neuron goes to this one, this value, and this one goes to this one. Okay, we are talking about these two things. Okay, first neuron we have taken it, and then so that is how it gives. And B1 is 1. Sorry, B1 is 0.35, right? So 0.35 into 1. Okay, and here if you solve this, this is what the Z value, right? Net H1. This is step 1. Net H1, it gives you 0. If you solve this one, you'll get approximately 0.3775. And this is now, if you write step 2, in step 2, what it does is it applies the activation function 1 divided by e to the power minus 0.3775. It gives you 0.593. You take, you do it in the Excel. Thanks, Swarna, to give this value. Okay. And step 1, and step 2. These are the 2 steps. So now this is the final output. So this is the sum of the product of each synapses value, each synapses weight with the corresponding input value. Okay. So it gives, and including the bias. Okay. If you add this, this is what your z value. 1 by 1 plus e to the power minus z. That is what your sigmoid function. Because for the sake of example, I've used a sigmoid function because we are talking about the churn analysis model. In that case, we want to predict the probability. The probability value should be anywhere between 0 and 1, right? So here, since we are using the sigmoid activation function, so it gives me the probability as point. So it gives me the value 0.593. So here, the output of this one is 0.593. We arrived this one. Okay, next we are going to, I just call this one as a net O1. Okay, net O1. I call this a net H1. Okay, and this is a net O1. Net O1, not 0, it is O1. So now this 0.593 needs to be multiplied with this one, and then we need to apply that one. So now what I do is net O1 is equivalent to W5 into out H1. Net H1 is nothing but the middle one. The output of the net H1 is this one, the out H1, right? Out H1. And W6 here, that is W6, right? Yeah, this is your W6. This is your W6, okay? So from here to here and here to here, all right? So, yeah, W6 into out H2, okay? Plus B2 into 1. So in this case, the W5, we know 0.593. Sorry, W5 is 0.40 into out H1 is 0.593. So this is the one. So in this case, what happened? Here, it goes from here to here, right? So this is the one. So W5 is 0. Okay, in this case, W5, right? So yeah, W6 here, W6 into out H2, 0.45 into out H2. So similarly, right, like how you have computed this one, similarly, if you do this one, you will get 0.596. Okay. So the out H2 is nothing but this one. Okay. Out H2 is this one. The output of this one. Okay. Out H2 is nothing but that one. Okay. 0.5968 plus the bias is 0.6 into 1. That is what we have seen. If you solve this, how much you'll get? Oh, can you please, can someone help me out? Swarna, Soumya, why don't you help me out? No? Yeah, what is that? Okay, okay. Sorry, here what we are talking is this one here. So this one and this one, right? So we are talking about net O1. So net O1, what the input comes, where the inputs comes from this one, right? Here and here also. This one, so like how you arrived this one, the same way if you apply, if you compute that, you will get this value. So this value into this value, and for this one, the weight is W6. Sorry, for this one, the weight is W6. And the W6 is nothing but 0.45 into 0.5968. And the bias is 0.60 for this one into 1. That is how we got this. You got it, Soundarya? Yes, that is how we got it. Yeah, very good. Thanks, Soumya. 1 point, how much you are getting? 1.05? 905. And okay, 1 divided by 1 plus e to the power minus 1.105 so sorry, 5905, right? Sorry, 905. Okay, so this one the step 1 we are done. This is your Z net-O1 or net-O1. Even in the net-O1, like in the hidden layer neuron, even in the output layer neuron, it performs two tasks. The one is this one, right? The sum of the product of all the corresponding synapses weight with the neurons, right? The previous neurons output value. And then once you get the Z value by performing the sum, right? You need to apply the activation function. After applying the activation function, how much are we getting? Excellent. 0.7517. So that is how we have arrived this one, right? This is your predicted value. This is your actual value. Okay, the actual value is something like this. Okay, actual value given by someone. After we have trained the model, this is how it is doing the computation internally, and it gives me the predicted value like this. To get this predicted value, you need to subtract from the actual value. If you subtract the predicted value actually, that is your error. And if the error value is very minimal, it doesn't require any further treatment. Okay, if the error value is, see, the whole idea here is we want to try to minimize the error as less as possible. Okay. So next one is, yeah, here they've given the EON, right? So right, this is the actual value, this is the predicted value. That is your error 1. Similarly here, you have the actual value and the predicted value. The same way, if you compare, so in this case, we need to take this one and this one, right? The output of this value 0.593 into this one. What is the weight of this one? See, W6 is this line, okay, and W7 is 0.50. 0.50 into 0.51968 plus 0.55 into this one, and the bias 0.60 into 1. Whatever that you get, that is what your out over. Okay, and you need to right? So now you need to subtract the EO1 value from the actual value. That is what your error, right? Error for EO2, right? Error for EO2. So in this case, so the formula for this one is, how do you find out the total error, right? So what is the metric for finding out the sum of squared error? 1/2 into, in this case, actual minus predicted whole squared. So in this case, we have two errors, right? Two neurons are there in the output node layer, and C1 plus E2. Okay, and this one gives me yeah, so here 0 point, yeah, good. So you have computed. So what she says, 0.77. How much, Swarna? 729, huh? Okay. 7729. So 0.1 minus that one, if you subtract it, you will get some value, right? So this is how, when I explain, if you people involve yourself and give me the answer, right? See, answer I can do it on my own. Where is the involvement? Simply if you watch, what is the use here, right? 1/2 into, very good. So everyone, I could see the contribution as well, 0.01 and minus 0.75136. This is even. So here we get the error is 0.274, right? 274. 0.274. This is for the E1, right? Similarly, E2. So can someone tell me what is the value for E2? All of you respond. Those did not respond, please type it in the chat window. Except Soundarya and Saumya, Praveen, including Raja, right? So others, I want others to respond quickly. Can you please compute the E2 value? What is the E2 error to value? Okay, 0 point. What is the value you are getting it, Swarna? E2 is equal to 0.023, right? Okay. See, I have given one example here. Same way you need to compute the E2. Yes, yes, you are correct. 0.0. Yes, there is a slight change, slight difference between the Swarna and Praveen's answer. Almost it is close by, maybe, right? Yeah. So 0.023. Very good. So we got the total error. So E1 plus E2. We need to add the E1 plus E2. That is what your total error, right? So E1 plus E2 is our total error. Got it? So what is the total error? 0.23 plus 0.274. That is what your total error. Okay, we got this thing. Now we wanted to minimize this error. Total error, we want to minimize it. That is where the back propagation comes into picture. The back propagation will traverse back here. It will traverse back, right? The feed forward is, the forward pass is something like this. The reverse is the back propagation. It will forward the error from the rear side to the immediate preceding neuron, and then this one will pass the computed value back to your immediate preceding input neuron. Okay, that is how it works. This is how the back propagation. Like I said, I gave you a one-liner answer. What is the back propagation? What is the whole idea of back propagation? The goal of back propagation is we wanted to minimize the error as less as possible. Even if you make it 0, it is good. Or else, right, try to minimize the error value as less as possible. That is the whole idea of back propagation. Okay, the statement is good. How can we do that, right? So certain things in life, right, it is easier said than done. But here, how do we do that? The same thing, right? How do we do that? So if you pass the values back, how does this happens here? See, the whole idea here is change the weights for each and every network or each and every synapse, weights for each and everything. See here what happened. Based on the weight only we computed the value, right? So weight 1 into this one, and here the 0.15, the weight is 0.0. Change these weights and then play around with it. After changing the weights, you check what is the error. See here, this is what the out H1. So this is what the final output, right? For these weights, for W1, W2, W5, W6, 0.4, 0.45, 0.15, 0.20, we are getting this value. So for W1, W2, W5, W6, we got this predicted value for these values, right? But if I use the, if I change the values for the W1, W2, W5, W6, instead of 0.15, instead of 0.20, instead of 0.40, instead of 0.45, how much, what is the predicted value am I going to get? If the predicted value is more, obviously, if you subtract that one from your actual value, see here I mentioned it here at 0.01. If you subtract this one from here, if the error decreases, then it is good. But it is not as easy as how we think, okay? So what value you can use it? By changing the value of W1, W2, W5 in this example, we can either minimize the error or it may increase the error also, right? So what values can be used for W1, W2, W5, and W6 such that the error can minimize? This is not a magical bullet, right? There is no magic. You cannot blindly tell some numbers, it will not reduce, right? If you try it manually, it takes a lot of time. If you try with different values for W1, W2, W5, W6, you will end up keep changing the values, and it will become an infinite thing, right? You will keep working on it. Still, you will not be able to arrive at the minimum value. It will take a lot of time. They have introduced something called backpropagation. So in the case of backpropagation, the idea is change the values, change different values, or use different values for W1, the weights, in such that find out at which W1, W2, W5, W6 weights value, this error is minimizing it. Error is getting reduced. So if I do it manually, it will go on and on, right? So that is, so they have come up with something like gradient descent algorithm. Gradient descent algorithm. Gradient descent algorithm. Using, in the case of backpropagation, the interview they'll ask you. So how does the backpropagation? Backpropagation uses something called gradient descent algorithm. With the gradient descent algorithm, we will try to find out the optimal values for W1, the weights. Optimal values for the weights. Once you obtain the optimal values for the weights with the help of the gradient descent algorithm, and if you plug in the value, your error will definitely should reduce. Okay. But if you randomly change the values for all the weights, and if you plug in the values here, and it'll go, it is going on and on, right? It is, there is no time bound for it. You'll have to keep changing it, changing it, changing it. It'll drive you crazy. Instead, they already came up with some algorithm to find out the optimal values for the weights. That is called your gradient descent algorithm, using which we can. Right. But in the case of gradient descent algorithm, we use chain rule and power rule, all the things. Don't worry, you don't have to read, a big, you don't have to read a big book, okay, to understand everything. I'll explain you everything in a very simple way. See here, if you look at logically here, so this error, right? The error, how did we get this error? From the auto one. How did we get this error? So for the source for this error is auto one, right? Auto one, right? What is the source for this one? This is the one, right? Since we have multiplied this hidden layers neuron value by the corresponding weight, and then we are adding this value, right? The same thing. We are multiplying this one with this weight. That is how we are getting it. See. So here net1, how we got this value for this neuron? For this neuron, how did we get this value? For this, we got the value, by multiplying this one, right? So for net1, we have used out h. Out h1 is net h1. So the output of this one, this one, right? The output of this one is dependent on this one, right? So this one is, the error is depending on the output values, and then output values, were depending on this one. This one is depending on this one. So I'm going to write something like this. So I'm going to take the partial derivative with respect to derivative. See, we need to find out. Now we will start with a simple thing. Okay. So this is a W5. I want to find out the optimal value for the W5. Okay. So how do I find out that? So for that, the error is depending on the output, right? For the source of the error is this one, right? Whatever the weights that used it, that is the one cause you to get this error, right? And this, for this, the source is this one, and for this, the source is this one, right? The out h1, sorry, the net h1. So here, we need to take the partial derivative on the error. Error is called cost with respect to W5 in order to get the optimal value for the weight W5. So now we are going to change the value for W5. Blindly, we cannot change it. We need to use the gradient descent algorithm. In the case of gradient descent algorithm, we need to take the partial derivative. How do we take the partial? We need to take the partial derivative of the error with respect to W5 if you want to get the optimal value for the W5. So this is not the straightforward. So here, so the dou E total, this is depend on your dou out 1, right? Or dou out O1. The previous layer, the error, the source of the error is depending on this one. So see, we are taking the total, we are taking the partial derivative with respect to out 1 with respect to E total into, see, the same things can be rewritten as like this, okay? And And dou out O1. So dou out O1, you won't take the partial derivative with respect to O2 1. With respect to what? Dou net O1. Right? And again, dou net O1 divided by dou W5. So here, this single thing, right? Partial derivative be to if you want to expand this one, you need to write it like this. So this error is depending on the out O1. The out one error for the out one, the source is net O1. For the net O1, the source is W5. Right? So here there are three things, three derivatives are there. We will now work on each and every derivative. So dou E total with respect to dou out A, dou out O1, dou out O1, dou out O1 is equivalent to, so what is this here? 1 by 2 into the actual minus predicted. So predicted is nothing but out O1, right? Out O1. Yeah, yes, Swarna, you're correct. Right? So the actual minus predicted. This is what I'm talking. The actual, this is what I'm talking, okay? Actual minus predicted. Whole square. So, and again, we have, out O2 also, right? Actual minus predicted out O2. Out O2 squared. So this one gives me the total error, right? This is the one gives me total error. In this case, we will have to apply the power rule. When you use the power rule, what will happen is the 2 will come here, 2 into 1 by 2, and then actual minus predicted out to 1, 2 minus 1. This is the power rule. The case of power rule, the squared value, whatever the value you have it here, right, to raise to the power, right, that one will come here, the front, and then you need to subtract 1 from this one. That is what your power rule. Okay, and then here, the second one, right? So here we are taking the partial derivative. So with respect to, so we, right, total error with respect to out to 1. We are taking out to 1. Since here we don't have out to 1, this will become constant. This one will become 1 here, right? So 1 minus, in this case, yeah, in this case, also what will happen? The 2 will come here. Right, so 2 will come here, 2 by 2 is, it will get cancelled. And this one will become minus 1, right? This one will become, since here we are taking the partial with respect to out to 1, right? We are taking the partial derivative on the total error with respect to out to 1. So in this case, the power rule is applicable. This one will come here, 2 into 1 by 2, a minus actually predicted value, 2 minus 1. And since we don't have out to 1, this one will become constant, or it will simply go away. Simply we can say, no, go away. It will become something like 1, nothing, okay? And you are left with only 2, this one and this one will get cancelled out. And we know what is the actual value, what is the predicted value. 0.01 is the actual, and the predicted value is 0. How much? Excellent, Swarna. Thanks for coming for my rescue. Instead of going back, right? 0. The first slide, 0.75136. You get 0.7413. This is your partial derivative on your total error with respect to dou out to 1, out to 1, out to 1. Got it? Any questions so far? See, yes. See here, this one, I want to find out the optimal value for the weight W5. In order to do that, I need to take the partial derivative on the total error with respect to W5. So for that, this one can be rewritten as something like that. For this, right, for this weight, if you want to change the weight, you need to take the partial derivative of the total error with respect to W5. This can be rewritten as something because the total error is depends, the source for this one is out TA, out 0, 1. For this, the source is net O1, the source is W5, right? With the weight of W5 and the net H1, net O1, you get the W5 error. So you get the error, right? So, with the combination of these three things only, you are getting it. So up to this, is it clear? Yes. So next, similarly, we need to find out, we need to write a derivative for this, and dou out O1, dou net O1. Okay. So in this case, how do you find out? It is slightly different for the second one. In the case of second one, this is for first one. This is for one, okay? This is for first one. The second one is, first of all, before we take the partial derivative, first of all, what is out over? Nothing but the activation function, right? The activation function. 1 second. So there is nothing but the 1 divided by 1 plus 1 divided by 1 plus e to the power net O1. All right, net O1. So if you take the partial, now if I take the partial derivative for this, dou out O1 divided by dou net O1 is nothing but the activation function, right? You are taking the partial derivative for the activation function is sigma into 1 minus sigma r. That's all. Simple, okay? Partial derivative for the activation function is this one. Since it's a straightforward one, so the sigma is nothing but in this case out to 1 minus out to 1. All right, so out to 1 is how much? 0.75136. 1 minus 0.75136. What value you will get? Can someone help me out? Thanks for now. 0.1. How much? 186. Correct? 0.75136 into 1 minus. See, in this case, out of 1 is pretty square, which is nothing but the activation function, sigmoid activation function. If you take the partial derivative on this one, this is the one. Okay. So how did we get this one? That requires a detailed explanation. Okay. So that requires another 10 to 15 minutes time. Let us not get in there. So the partial derivative for your activation, sigma activation, sigma into 1 minus sigma. That's all. Okay. This one is it's nothing but the activation function, right? Auto 1 into 1 minus auto 1. So this one is the output of this one is the activation one. The activation output is nothing but the auto 1, right? So if you multiply, you get this one. We got the answer for the second one. See, for the second one, we got the answer, and first one, we got the answer. And now we need to find out the partial derivative for this one. How do you find out? So in this case, I just go here. For the third one, 1 second. For the third one, so for the third one, first of all, before we do that one, net O1, what is net O1? W5 into out H1, W6 into out H2, plus bias, right? Bias into 1. So here, if you take the partial derivative, dou net O1 divided by dou W5, so what you will get here? So here the W5 and okay, we are taking the partial with respect to W5. What is the coefficient of W5? So the 1 into W5 is W5. So whenever you take the partial derivative with respect to the specific value, in this case W5, so you need to look at the W5. What is the corresponding other value attached with this? So 1 into W5 is W5, right? Since 1. When you take the partial derivative, with respect to W5, right? When you take the partial derivative for net O1 with respect to W5, you need to check where and all W5 is there. So in this case, W5 is there. The corresponding, you see, if you have 2 here, it will be 2. But here nothing is there, hence W5 into 1 is the, W5. The 1 is the coefficient for this one. You need to take only 1 here. And then what else we have? Into 1 into out H1 plus what other value we have it here. So the next one is the out H2 plus bias 1, right? So in that case, W6, right? Since we don't see W6 there, what will happen? Since we are taking the partial derivative of the net one with W5, we need to see W5, right? The rest of here we don't have the W5 at all. Instead, W6 is there. Hence, this one will become constant. These terms will get cancelled out, and we are end up having only this value, right? So if you solve this one out H1, you get only out H1. In this case, you will get only out H1. You will get only out H1. What is out H1? What is out H1? So now we need to plug in all these values, 1, 2, 3. We need to plug in all these values. And if you multiply this one, you will get the optimal value for your weight W5. Weight W5. Got it? See, this out H1 we already computed, right? Out H1, did we compute it here? Not here. Okay, so now we are done with 1, 2, 3, right? For each and everything, we have written the for partial, we have taken the partial derivative for each and everything. We have plugged in the value, and then we got the output. Out H1 is the output of your this one, this layer, right? Out H1 is this one. That is what the thing, right? So that's all. So right. So whatever, if you multiply 1, 2, 3, what is 1 here? 1 into 2 into 3. What value you will get? So 1 is your, for the first one, right? 0.7413. 0. Excellent, right? See, 0.743. The second one is 0.186. And out H1 is nothing but your the output of out H1 is this one, 0.593, right? 0.593. See, out H1 is not this one, sorry. Out H1 is this one, right? Out H1. If you multiply these three values, whatever the value that you get it, that is what the new weight for W5. I told you, how to reduce the error. In the case of backpropagation, the idea is change the existing values of the weights, all the weights in your neural network from the rear side, and see if the error is reduced with the changed values for all the weights. If it is not, then you need to iteratively keep changing the values. So now, but now the question is, how can I find out the optimal value? But if I keep changing the values for W5, it will go on and on, right? It requires a lot of time. So, right, I don't want to get into that one. But that is when we have used something called gradient descent. As part of that, we have something called chain rule. With the help of chain rule, what we did, we have rewritten this one as like this. Because for the out to one, so we won't take the partial derivative of the total error with respect to W5. But in this case, the total error is depending on out to one also. Okay, and then the out to one, the source is net O1, net O1, the source is W5. Okay, and once you derive this, you need to find out the values for each and everything. Okay. And you need to take the partial derivative for total error with respect to out A, out O1. You need to take the partial derivative for out O1 with respect to net O1. You need to take the partial derivative for the net O1 with respect to W5. And if you multiply all these values, you will get some value. That is what the change value for your weight 5. Similarly, if you do it, if you follow the same steps, right, you will find out the value for the W6, W7, right? And then you need to pass that value back to this one till the source. Once you get the value, once you get the new value for W1, W2, W3, W4, W5, W6, you need to plug in the values and see if your error got reduced. If your error was not reduced, again you take the partial derivative, same thing, and plug in the value. Here, the actual minus predicted. So in this case, the actual is, the predicted is 0. This one will be the new predicted value based on the changed W5 value or W1, W2, W3, W4, 6, right? So you need to keep iteratively doing this until your error becomes minimum. Okay, so now you understood what is the idea of backpropagation? What algorithm is used in the case of backpropagation, gradient descent algorithm. So I have taken a simple example, only one weight I have taken, W5. So for W5, how can I find out the value for the W5, optimal value for the W5? So for that, you need to take the partial derivative of the total error with respect to W5. And if you do this, if you expand this one, you will get this one. And if you if you take the partial for each and everything, you will end up something like this, right? So 0.7413, 0.1 and minus 23. If you multiply this, whatever value you get, that is what the new value for your W5. Similarly, you compute the value for W6, W1, W2, W3, W4, W6. That value you plug in, and then you find out the error. If the error is still not that minimal, again you need to find out the optimal level. Do repeat the same step until you get the very less error. If your cost is very low, you need to iteratively change the values for the weights. Okay. So this is all about backpropagation algorithm. Okay, I made it very simple. Okay, so how can I implement backpropagation in neural network? You don't have to do that. Fortunately, the cross, right, in the neural network model, yesterday I showed you, right? It takes care of it on its own. Okay, we don't have to do it explicitly. For example, here, the backpropagation, only thing is the interview, they'll ask you, how does this work? Can you explain me? You can explain this way, right? So I need to take for example, I have two neurons are in my output layer. I call out to O1, out to O2. For out to O1, if I want to find out for the out to O1, the source for the out to O1 is the W5. I want to find out the weight, optimal for the weight. I need to take the partial derivative for the total error with respect to the out to O1. And also I need to take the partial derivative of out O1 with respect to net O1, and then net O1 with respect to W5. I need to take it. So that one will give me the optimal value for the W5. But in this case, we need to take the partial for each and every value in order to get the optimal value for the W5. 1 second, I will. And if you remember it, okay, chain the channel analysis, right? In channel analysis, yesterday I explained you the Keras. What is Keras? Keras is an API to your TensorFlow. It is an interface to your TensorFlow. And, right, there we have created the sequential model, and then we have sequentially stacked the layers one after the other. Input layer, hidden layer, output layer. We have used it. That's all. And then model dot compile. So in there we mentioned about the optimizer, everything, right? So back propagation is taken care automatically. We don't have to write anything, we don't have to include any additional lines of code. Okay, while compiling it, it does the back propagation, everything, and then only it gives us the predicted values. See here, I go here, Keros. So here, if you see, right, the sequential, so the model dot, all you need to just say, binary cross and entropy. Loss is nothing but your cost. Okay, which error function can use binary cross entropy? That's all. Optimizer is so instead of gradient descent, we have something called stochastic gradient descent. The difference between gradient descent and stochastic gradient descent, in the case of gradient descent, what happens is for each weight, for each iteration, it takes the entire data set to find out the value for each weights. Supposing you have 1 million records, for every iteration, right, it has to take the 1 million records to find out the value for W5. Okay. So instead, they came up with some stochastic gradient descent. In this case, it takes only one value. With that, it fits the model. Okay. With that, it tries to reduce the error. Okay. Only one record. Okay. So metrics is accuracy. That's all. It takes care of everything. Okay. It does the back propagation, everything. And then, sorry, when you do the model fit, when you do that, so you compile the model and then model fit, it trains the model. Okay. It trains the model. And so here what happens is it does the back propagation, everything. That's all. Okay. We don't have to do the back propagation explicitly. Hope you understood what is back propagation, what is gradient descent. Okay, there is a question from, yeah, that's a good question. Deepa's question is, what is chain rule, sir? Can you explain chain rule? But I could see that in the net chain. Yeah, I will explain you chain rule. See, chain rule is something like something like this. I will just make it. Supposing you have a function, okay, you have a function something like this. Y is equivalent to 2x plus 1 to the power 6. Okay. You want to find out the partial derivative for y. Okay. So dou y, here you want to find the partial with respect to x. Okay. So in that case, what will happen is, in the case of chain rule, first you need to take the derivative of the outside function and then you need derivative of inner function. So I just write it here, derivative of outside function into the derivative of inside function. So what is the derivative here? So the derivative of outside function. See, this is inside function. The outside function, we don't have anything. But here, what we need to do, you need to bring this squared value, right? This is the 2x plus 1 raised to the power 6, right? You need to bring that to the front. Okay, 6 into 2x plus 1, 6 minus 1. Okay. And here, if you solve this, what value you will get it? So since we are taking the partial derivative of y with respect to x, right? So here the coefficient for this one is 2, right? 6 into 2, 12. And this one is constant, it will go away. Here you will get 12. So the derivative of inside function into derivative of outside function. The outside function is, we don't have any value. But in this case, right, we need to use power rule also. So this one will come, the raised to power, right? That one will come here. You need to subtract 1. And if you take, since you are taking the partial derivative of y with respect to x, wherever x is there, you need to take the coefficient, corresponding coefficient value. The coefficient value is 2. So only 2 will remain here. 6 into 2 is 12. Yeah, 12. Yes, this one. What about the, yeah, you are correct. 12 to the power 6 minus 1 is 5, right? 12 to the power 5. Right, that is what you will get it. This is what, this is how, so in simple terms, they ask you chain rule. What is chain rule? You tell them the derivative of outside function into derivative of inside function. For example, y is 2 is plus 1 to the power, raised to the power 6. Take the 6, here, and then 2x plus 1, identify the inner function and the outer function, and then the derivative of the outer function, leaving the inner function. Find the derivative of the inner function. You need to multiply the results from both, okay? And right, this is the one, this is nothing but your chain rule. Any other question? Why should I take partial derivative all the things? See, in the case of gradient descent algorithm, you have to take the partial derivative. So partial derivative, so you need to take the partial derivative. For that, we will be using the chain rule, right? We need to take the derivative of the outside function first, and then you take the derivative of inside function. Okay, you need to take the partial derivative. That's the only way of you are using gradient descent. The whole idea of the gradient descent function is want to reduce the weight. Okay, that's all. Any other questions? Okay, since you don't have any questions, I'm going to wrap up this session now itself. Okay, and I would